In the Marvel Cinematic Universe, reality breaks all the time. Timelines split. Universes collide. Small changes create entirely different worlds. A single mistake can rewrite everything. At one point, a character even offers a theory that sounds almost poetic. Dreams are windows into the lives of our multiversal selves. In that universe, the scenes you visit at night are not just inventions of your mind, but brief connections to other versions of you, living out different histories in different worlds. We watch this as fiction, entertainment designed to impress us with spectacle. But what if the idea behind it is not entirely fictional? In real science, physicists now seriously discuss the multiverse, the possibility that our universe is only one among countless others. Quantum mechanics suggests reality can exist in multiple states at once. String theory proposes hidden dimensions folded into the fabric of space-time. Black holes bend reality to its limits. Time itself does not flow as steadily as we once believed. At the same time, ordinary people experience moments that feel off, shared memories that never happened. Lost time, déjà vu, events that seem to ignore cause and effect. We usually explain them away as coincidence or psychological error. But what if these moments are the real-world equivalent of what the MCU calls timeline glitches? This video explores a disturbing possibility, that reality is not a single, continuous world, but a constructed system, one that sometimes malfunctions. Stay until the end. Because if reality can glitch, then the question is no longer whether fictional universes exist, but whether we are already living inside one. Suppose that possibility does not disappear when the video ends. It just sits there. Like a small error message, your mind keeps trying to close, only to find it quietly reopening in the background. You go back to ordinary life, to the routines that usually feel solid. You wake up, check your phone, drink something hot, answer messages, move through rooms that you know by heart. Nothing supernatural happens. No objects vanish. No portals open. And yet, every now and then, reality misses a beat. It is almost always small when it happens. You put your keys on the table. You turn away for a moment. You turn back, and they are somewhere else. You are certain you did not move them. You walk through a street you have walked 100 times. And for a few seconds, everything seems fractionally misaligned, as if a familiar melody were being played half a note off. You see a stranger whose face you remember with the deep familiarity usually reserved for people you have loved, and yet you are sure you have never met. We normally file these moments under familiar labels: stress, distraction, fatigue, faulty memory. The brain, after all, is not a perfect recorder of events. It is closer to a storyteller that fills gaps, stitches fragments together, and quietly edits anything that does not fit the ongoing plot. When you forget where you left your phone, you do not treat it as a cosmic event. You treat it as a small, temporary failure of the narrator inside your head. But if doors to other dimensions existed, they would not declare themselves with thunder. A door that could connect one branch of reality to another, one timeline to another, would not need to fling cars through the sky or rewrite continents. A door like that could be microscopic and brief. It could feel exactly like a misplaced object, a skip second, a memory that does not match what everyone else recalls, something too trivial to count as evidence, but too sharp to feel like nothing. When physicists talk about dimensions, they do not mean magical planes of existence stacked like levels in a video game. A dimension is simply an independent direction in which something can vary. We are used to 3 directions in space: left and right, forward and back. up and down. Time feels like a fourth, moving us from earlier to later. If there were additional dimensions, they might not be places we can visit. They could be hidden ways the universe is structured, folded so tightly that our senses never notice them. A door into such a hidden structure would not look like a glowing portal. It might look, from our perspective, like a local error in how things usually unfold. Human history is dense with stories of such errors. People speak of losing hours on a drive that should have taken less than one, of seeing a craft in the sky that moves in ways no known aircraft can, of hearing footsteps in an empty house, or seeing someone standing at the foot of the bed who vanishes when the light is turned on. From one angle, these are classic examples of how perception can mislead us. From another angle, they are reports of the same basic sensation, the sense that the world temporarily stopped behaving according to its own script. To treat every strange experience as supernatural would be reckless. Our brains are vulnerable to illusions, biases, and expectations. When you remember your childhood, you are not playing back a recording, you are reconstructing it, over and over, influenced by later knowledge, by emotion, by the way you tell your own story. When large groups of people vividly remember the same event that never happened, we do not need a broken timeline to explain it. We need to understand how remembering itself can be a form of imaginative editing. But there is a deeper discomfort hiding underneath the psychological explanation. If the only access you have to reality is through your senses and your brain, then your certainty about an external world is always indirect. You never experience the universe as it is. You experience the universe as it appears, after being filtered, compressed, interpreted, and sometimes distorted. This is true when you see a ghost, and it is just as true when you see your own hand. The difference is that one experience matches your expectations and the other does not. The idea of a reality glitch does not have to mean that the universe literally crashed for a moment like a computer program. It can simply mean that the smooth story you tell yourself about the world shows a crack, your assumption that events follow one another neatly, that causes led to effects in an orderly chain, that your memory provides a stable anchor, suddenly feels less secure. For a brief moment, you are forced to confront how much of your life is built on trust in patterns that you cannot fully verify. If our universe were a constructed system, a kind of large-scale simulation running on some deeper physical or informational substrate, glitches would be an expected side effect in many imagined designs. In a digital environment, objects are not infinitely continuous. They are represented by discrete pieces of information, updated in steps. Most of the time, those steps are so small and frequent that the world appears continuous. But under strain, or in regions that are rarely visited, or when the system is reconfiguring itself, you might see artifacts, a frame that freezes, a texture that fails to load, a character that appears where it should not be. Of course, our world does not show us obvious pixels or frozen frames. If there are limits to its resolution, they lie far beyond what our eyes can detect and what our everyday tools can measure. But the concept is useful as a thought experiment. Imagine that you were a character in a game world. How would you distinguish between an error in your own perception and a glitch in the underlying system? You would have no access to the code. You would have no way to step outside the game and look at it from the outside. All you would have are patterns inside the world itself and your own fallible attempts to make sense of them. This is where the unsettling part begins. The question is not simply whether some strange event was real or imagined. The question is how you would ever know, in principle, that you are not living inside a constructed environment, when the only tools you have to test reality are themselves part of whatever reality is. There is a circularity you cannot escape. Your experiments, your measurements, your theories, your memories, your instruments, your nervous system, Everything you use to probe the world is already inside the thing you are trying to understand. In ordinary life, we do not dwell on this. We act as if the external world is solid and self-sufficient. We treat an object as something that continues to exist, whether or not we are looking at it. We trust that the floor will not vanish under our feet. This trust is not ridiculous. It is a practical necessity. You could not function if you had to question the existence of every coffee cup before you picked it up. And yet, when reality seems to miss a beat, even in small ways, it briefly exposes how much of that trust is a choice. Moments of dissonance do something else as well. They bring you face to face with the fact that you will die without ever having a final, external confirmation of what this world really is. Whether it is a simulation or a physical universe or something stranger than both, you will only ever know it from the inside. Your questions will outlast you. Your theories will be updated by people who never knew your name. The system, whatever it is, will continue without you. For some people, that feels liberating. For others, deeply unfair. For many, it is simply uncomfortable. So when someone tells a story about a vanished hour on a lonely highway, or a repeating number that follows them through life, or a dream that spills into waking reality, the most interesting part may not be whether the event happened exactly as described. The most interesting part may be the way such stories quietly express a deeper intuition, that the world might not be as self-contained as it seems, and that our sense of belonging in it is more fragile than we admit. We can dismiss individual accounts. We can explain many of them with known psychology. But the recurring feeling they encode, the sense of a script breaking, is harder to erase. It is the feeling that you might be inhabiting a system that is not built with you in mind. A system in which you are free to move, to choose, to care, and yet never fully able to see the machinery that makes any of that possible. In that sense, a reality glitch is not just a strange event. It is a brief, troubling glimpse of how little control you have over the most basic question of all: what kind of world this really is. If the world you inhabit might not be self-contained, one natural next question is whether it is even unique, whether this is the only stage on which reality can play, or just one room in a structure that does not end with your sky. Physicists have a word for this larger structure. They call it a multiverse. The term sounds like marketing, or like the premise of a superhero franchise. But underneath the glossy surface, it points to a simple, almost modest idea. Instead of a single universe with one history and one set of physical rules, there could be many universes, each with its own history, its own conditions, and perhaps even its own definition of what counts as matter, space, or time. To understand how anyone could say this with a straight face, you have to go back to the earliest moments after what we call the Big Bang. According to a family of theories known as cosmic inflation, the universe went through a brief phase of extremely rapid expansion very soon after its birth. Not just fast in the everyday sense, but fast in a way that breaks your intuition. A tiny region of space, far smaller than anything you could see, grew to cosmic size in an instant that was shorter than any blink you can imagine. This idea was not proposed to sound dramatic. It was introduced to explain puzzles about why space today looks so uniform and so delicately balanced. The basic idea is this: if space is filled with a kind of energy that pushes outward in a steady way, then that energy will make space expand faster and faster, smoothing out irregularities as it stretches them apart. Inflation is the name for this runaway expansion. When that special energy eventually decays into ordinary particles and radiation, the inflation phase ends, leaving behind a hot, dense universe that then continues expanding more gently. That gentler expansion is the one we now observe. So far, this may still sound like a single universe story. One burst, one inflating region, one resulting cosmos. But many versions of inflation theory have an extra twist, The process that ended inflation here does not have to end everywhere at once. In some places, the special energy decays and creates a universe like ours. In other places, inflation keeps going. New pockets of space peel off and stop inflating at different times, each becoming its own bubble universe, while the overall inflating space continues to spawn more bubbles without end. This picture is sometimes called eternal inflation, and it turns the universe into something like a foam of bubbles growing inside a medium that never stops expanding. Inside each bubble, the inhabitants would experience something that feels like a complete universe. They would see galaxies, stars, perhaps planets, perhaps life. Beyond their cosmic horizon, beyond the farthest light they could ever see. Other bubbles would exist, but remain forever inaccessible. From the inside, a bubble feels like everything. From the outside, it is just one region among many. The Marvel films take this idea and turn it into something you can visualize. In those stories, there is an Earth with superheroes, and there are other Earths with different histories. One world where a character died, another where they lived, another where they were never born. The filmmakers draw branching diagrams of timelines, each branch representing a different history that unfolds from a single point of divergence. They give some of these worlds names and numbers, like Earth 616, to suggest a vast catalogue of alternate realities. For entertainment, this is neat branding. From the point of view of physics, there is something unexpectedly close to the truth in the underlying picture. If inflation really spawned countless bubble universes, then the idea of many histories is not just fiction. It becomes a natural consequence. In some bubbles, the values of the basic physical constants might be slightly different, leading to universes where stars live shorter lives, or where atoms are less stable, or where chemistry does not support anything like biology. In others, conditions could be similar enough to ours that galaxies and planets, and perhaps even something like humans, arise. Whether exact copies of you exist is a subtle and unsettled question. But the notion of many cosmic branches with different outcomes is not just a comic book device. It is one way our best theories can be read when pushed to their logical edge. Still, it is important to keep the picture clear. When Marvel shows characters leaping from one universe to another through glowing gateways, that is pure narrative convenience. In eternal inflation, different bubbles are separated by regions of space that are still inflating so quickly that no signal can cross from one bubble to another. Each bubble is encased behind an effective barrier of stretching space. There are no doors you can step through, no magical platforms that let you pick which universe to visit. The similarity lies not in the travel, but in the concept of a landscape of many worlds, each with its own consistent history. To make this more concrete, imagine you are standing in a vast fog. You can only see as far as the light from your torch reaches. Everything beyond that radius is hidden. You could believe that nothing exists outside your circle of light. Or you could allow for the possibility that the fog continues, and that other circles of light exist elsewhere, each centered on someone else. In cosmology, your circle of light is your observable universe. It is the region from which light has had time to reach you since the beginning of cosmic expansion. The multiverse idea says that beyond that sphere, other regions exist with their own observers and their own skies. You will never see them, but their existence is not ruled out by the equations that describe the fog itself. The moment you accept that possibility, even tentatively, something interesting happens to your sense of what is fundamental. You can no longer say that the laws of physics you measure here are the only way reality can be. They may just be the rules in this bubble. Elsewhere, the underlying theory might allow different stable arrangements of fields and forces, leading to different apparent laws. In that context, what you call a constant of nature starts to look more like a local setting. In Marvel's depiction of the multiverse, this becomes a visual motif. You see familiar landmarks rebuilt in strange colors. The same city with different rulers. The same character with shifted personality or fate. Underneath the spectacle, there is a kernel of a serious idea. If reality is vast enough and has many regions with slightly different starting conditions, then small differences at the beginning can lead to huge differences later on. A tiny variation in initial density can change the way galaxies cluster. A slightly stronger or weaker force of gravity can determine whether stars live long enough for complex life to evolve. In that sense, the films capture something that physicists quietly accept, that our universe could have been different in ways both minor and profound, and that nothing in our current theories demands that only this particular set of conditions exists. Most people are willing to treat this as an abstract possibility. Fewer are comfortable tracing out its implications for meaning. If there are unimaginably many universes, where every allowed configuration of matter and events is realized somewhere, what happens to the weight of your choices? Does it matter that you decided to move to a new city, to end a relationship, to forgive or to refuse forgiveness? If in some other branch a version of you did the opposite? This is where the question stops being purely physical and starts brushing against how you live with yourself. Some thinkers argue that if every possible outcome is realized somewhere, then individual decisions lose their seriousness. Others point out that you never experience those other branches. You only ever live inside this one path, with its particular consequences and its particular regrets. Even if the multiverse exists, you are still the one who has to wake up inside this specific world with the memory of what you did. In that sense, your responsibility does not evaporate. It becomes strangely localized. You are responsible not for all possible versions of you, but for the one you wake up as each day. In terms of physics, the multiverse also shifts what we mean by explanation. Traditionally, if we observed that some property of the universe seemed finely tuned for life, we would search for a deeper law that forces that property to take exactly that value. In a multiverse setting, a different kind of explanation is on the table. Perhaps the underlying theory allows many possible values, realized in many universes, and we simply find ourselves in one of the rare universes where the values happen to allow complex structures. This is sometimes called an anthropic explanation, after the simple fact that any observers can only arise in regions where conditions permit their existence. This style of reasoning makes many scientists uneasy, because it can feel like giving up on more traditional forms of testable prediction. After all, you cannot easily observe other universes to check whether they exist or what their properties are. You can only infer, indirectly, that if inflation and certain high-energy theories are true, then a multiverse might be a natural byproduct. You can test pieces of the framework, like the behavior of cosmic background radiation or the distribution of galaxies. But you cannot look over the fence into a neighboring bubble. Marvel, in its own way, acknowledges this blindness. For all the jumping between worlds, the characters still have no access to a vantage point outside the entire multiverse. There is always some higher layer of authority hinted at, some incomprehensible design or beyond. In a more sober sense, this mirrors our situation. We can write equations, build colliders, launch telescopes, and still we are working from inside one tiny region of a reality that may be far larger and more varied than we can ever see. If you place the multiverse idea next to the possibility of simulation, something even stranger happens. A simulated world does not have to contain the entire multiverse. It might only represent one specific bubble, or even just one narrow slice of one bubble. But if the deepest laws of the simulating reality themselves allow a multiverse, then our bubble could be a simulation of a universe that is itself just one branch inside a bigger structure. The levels stack. The notion of a single, ultimate base reality recedes. You get, instead, a nested architecture of worlds within worlds, each obeying its own consistent rules. each containing beings who can ask whether their world is the only one. None of this is established fact. The multiverse remains a speculative extension of theories that are themselves well supported but not complete. Many researchers work on alternative approaches that do not require multiple universes at all. The important point for us is not to decide which side is right. It is to notice that once you follow our best current theories to their edges, you are naturally led to pictures of reality that do not look like a single, solid block. That realization alone is enough to loosen your grip on the idea of one true, simple world. Even if our universe turns out to be unique, the fact that we can coherently imagine and mathematically describe a vast space of possible universes should give you pause. It suggests that what you call reality might be less like a singular object and more like one realized instance in a much larger catalogue of ways things could be. Whether that catalogue exists physically, or only in equations, or only in the structure of our theories, is still open. But once you see the shelves, it is hard to go back to believing that your particular book is the whole library. If reality can multiply at the scale of whole universes, it is natural to wonder what happens when you zoom in instead of out. When you stop thinking in terms of galaxies and start thinking in terms of single particles and single moments, because long before the word multiverse appeared in films, physics had already discovered something far stranger, a kind of branching that happens not in distant bubbles of space, but in the quiet interior of every measurement you make. In everyday life, objects behave in ways that feel reassuringly simple. A coin is either heads or tails when it lands. A chair is either in the room or not. A person is either here or there. We are used to the idea that things have definite properties, whether or not anyone is looking. When we do not know some fact, we assume the fact already exists. We are just ignorant of it. The world, in this picture, is like a book that is already written. Reading reveals what is there, but it does not change the story itself. At the quantum scale, this picture breaks. Quantum theory was born to explain phenomena that refuse to fit classical expectations. When scientists studied light and matter at very small scales, they found that particles sometimes behave like tiny, localized dots, and sometimes like extended waves that can spread out and interfere with themselves. To make sense of this, they introduced a mathematical object called a wave function. The wave function is not a wave of water or air. It is a wave of possibilities. Where its value is large, the theory says you are more likely to find the particle there. If you look, where it is small, the particle is less likely to be found. The strange part is this: before you look, the wave function does not single out one actual place. It represents a superposition of many possible outcomes existing together. Superposition, in simple terms, means that a system can be in several mutually exclusive states at once. A particle can be in a superposition of here and there. An atom can be in a superposition of excited and not excited. A photon, a particle of light, can be in a superposition of going through one path and another path at the same time. An old and famous example of this is the double-slit experiment. Imagine a barrier with two narrow openings and a screen behind it. If you send tiny particles, one at a time, toward the barrier and detect where they hit the screen, you might expect them to form two bright bands, one behind each opening, like grains of sand thrown through two windows. Instead, if you do not check which opening each particle uses, what appears on the screen is an interference pattern, a series of bright and dark stripes, as if waves had traveled through both openings and combined. Each individual particle seems to behave as if it went through both slits in a superposition, interfering with itself. But when you place detectors to find out which path it took, the interference pattern disappears, and the particles land in a way that looks like simple, classical choice. The act of observing seems to change what is happening. This is not just a story about our ignorance. It is not that the particles secretly chose one slit and we just did not know which. If that were the case, the interference pattern would never appear. The mathematics of quantum theory, which has passed every experimental test so far, tells us that before measurement, the particle genuinely exists in a superposition of possibilities. After measurement, we always see a single definite outcome. The question that haunts physicists and philosophers is what exactly happens in between. The standard textbook way of talking about this involves two kinds of evolution. When a system is left alone, its wave function evolves smoothly according to a precise equation. When a measurement happens, the wave function is said to collapse, randomly selecting one outcome with a probability determined by its shape. Collapse is not described by the same smooth equation. It is added as a separate rule. We do not see collapse as a physical process. We just see that before we look, there is a spread of possibilities, and after we look, we record a single result. This is called the quantum measurement problem. It is the puzzle of how and why the indefinite realm of superpositions gives way to the definite world of experience. Does consciousness play a role? Is there some hidden variable we are missing? Does the wave function represent reality itself, or merely our knowledge about it? Different interpretations answer these questions in different ways. While all agreeing about the statistical predictions for experiments, one of the most radical, and at the same time most austere, answers is the many worlds interpretation. Its basic move is simple. It refuses to add the collapse rule. Instead, it takes the smooth equation that describes the evolution of the wave function and declares that it always applies, even during measurement. When you measure a quantum system that is in a superposition of several outcomes, the combined wave function of you plus the system evolves into a superposition of several branches. In each branch, the system has a definite result. And so do you. One version of you sees the particle land here. Another version sees it land there. The branching is not something you notice from the inside, because each version only remembers one outcome and has no direct access to the others. From this point of view, the universe does not collapse. When you look at it, it splits. The wave function of the entire universe is a vast superposition of countless branches, each representing a different history. Whenever a quantum event with multiple possible outcomes interacts with something macroscopic, the branches become effectively independent, a process known as decoherence. Decoherence means that the different branches stop interfering with each other because information about the outcome leaks into the environment in a way that cannot be reversed. It is like splashing ink into water. You can no longer gather it back into a single clean drop. If this is correct, branching is happening everywhere, all the time, not just in laboratory experiments. Every interaction that amplifies a quantum uncertainty into a classical difference creates new branches. The atmospheric molecule that happened to collide with a dust grain in one way rather than another, the neuron that fired slightly earlier or later than it might have, the radioactive atom that decayed during your walk instead of waiting until after you passed. Each event nudges the future into one of many possible paths, and each path, in this interpretation, is realized in a separate branch of the universal wave function. It is tempting to translate this into the language of personal decisions. Every choice you make creates a new world. That picture is not entirely wrong, but it can be misleading. Your conscious decisions sit on top of an ocean of microscopic processes you do not control. The many worlds picture does not give your will magical creative power. Instead, it says that what you experience as a single, continuous life is just one thread in a larger tapestry woven from all the ways those microscopic processes can go. When you stand at a crossroads and choose one path, you feel the weight of that choice precisely because you are the one who will remember it in this branch. In other branches, versions of you with slightly different histories walk away under different skies, unaware of you. just as you are unaware of them. There is a quiet, unsettling honesty in this view. It does not comfort you with the idea that your preferred outcome is somehow specially selected. Every allowed outcome happens somewhere. From an external vantage point, if such a thing existed, nothing is lost. But from your internal vantage point, everything still matters. You only get one sequence of memories. You only experience one arc of regret and relief. The fact that other versions of you exist in other branches does not cancel the particularity of this one. It just denies that this particular path is all there is. Technically, many worlds is not an extra theory piled on top of quantum mechanics. It is a way of taking the existing mathematical formalism at face value and refusing to add any new rules. That simplicity is part of its appeal. At the same time, it asks you to accept an enormous multiplication of unseen reality. Every measurement, every scattering of particles, every fluctuation of fields, all giving rise to new branches. You will never meet your other versions. You cannot send messages across the split. The branching is, for now, a picture rather than an experimentally distinguishable fact. Other interpretations make different trade-offs. Some introduce hidden variables that fix outcomes behind the scenes. Some modify the equations to include an objective collapse that happens spontaneously beyond a certain scale. Some treat the wave function as a tool for calculating probabilities, not as a direct description of reality, and say that asking which outcome is real before a measurement is simply a wrong kind of question. All of these views reproduce the same statistics we measure in experiments. The science does not tell you which story about reality to believe. It forces you to live with several coherent but mutually incompatible ways of understanding what those statistics mean. At this point, the familiar ground starts to give way. In ordinary life, when you say that something happened, you mean that one sequence of events took place and others did not. You take for granted that there is a single history, even if you do not know all the details. The quantum picture refuses to endorse that assumption unreservedly. Depending on how literally you take the mathematics, reality may be fundamentally about a structure of coexisting possibilities, with our experience of a single world emerging as a special, limited perspective on that structure. This is not just a technical curiosity, it reaches into how you think about your own existence. If every serious interpretation of quantum theory forces you to accept that the line between possibility and actuality is not as simple as it feels, then your confidence in what it means for something to be real starts to loosen. You still have to live, to choose, to care. You still feel the weight of your decisions and the finality of irreversible events. But in the background, there is a new kind of doubt, not the shallow doubt of conspiracy, where someone else secretly controls the world, but a deeper doubt about whether the concept of a single, definite world ever made sense at the most basic level. You will never stand in a lab and watch universes split like soap bubbles. You will only ever see one outcome at a time. Yet the mathematics that predicts those outcomes with uncanny accuracy invites you to imagine a reality in which the unseen majority of what exists is forever beyond your reach. A reality where what you call the present moment is just one thin strand in a vast, branching structure that has no privileged center. And somewhere between the equations and your everyday sense of self, the quiet question returns. When you say that something really happened, what exactly do you think that means? That question becomes even less stable when you realize that our idea of a world is already shaped by something we rarely inspect, the way we picture space itself. The stage you think you stand on may be much larger and much stranger than the slice you can move through. When most people think about dimensions, they imagine directions, left and right, forward and back, up and down, 3 independent ways to move, 3 coordinates to fix your position, 3 axes to describe where something is. Time adds a kind of 4th direction, but it feels different. You can move freely through the three directions of space. Time moves you, whether you consent or not. This picture is so natural that it is easy to forget it is a picture at all. In physics, a dimension is not a mystical plane. It is any independent parameter you need to describe what can change. If you live on a flat sheet, like a drawing on paper, you only need two numbers to say where you are, how far along and how far up. You are a two-dimensional being. You could slide past other shapes, turn corners, draw circles, but the idea of above the paper would mean nothing to you. If a hand reached in from the air and lifted one of your neighbors off the page, you would not see a smooth ascent. You would see a shape simply vanish. This is the key intuition behind stories of higher dimensions. They are not necessarily far away. They can be here, but oriented in directions you cannot move. Just as the flat drawing cannot look up, you might not be able to look into a direction beyond the familiar three, even if it is as real as length and width. String theory takes this seriously and turns it into mathematics. At its core, it is an attempt to describe all particles and forces, not as point-like dots, but as tiny strings of energy that vibrate in different ways. Different vibrational patterns correspond to different particles. Much like different notes on a violin string come from different ways the string can move. For this idea to work consistently without mathematical contradictions, the equations require more dimensions of space than the three you know. In many versions, they require 9 spatial dimensions, plus 1 of time. In a larger unifying framework, often called M-theory, the full picture uses 10 spatial dimensions, plus time, for a total of 11. These extra dimensions are not speculative decoration. They are built into the way the theory avoids impossible infinities and keeps particles from misbehaving on very small scales. But if they exist, why do you not see them? The usual answer is compactification. The idea is that the extra dimensions are curled up so tightly that you can move through them only in an unimaginably small range. A common analogy is to picture a garden hose. From far away, it looks like a one-dimensional line. Move along it and you have one obvious direction. But up close, you see that the hose is not a line at all. It is a cylinder. An ant crawling on its surface has 2 directions of movement, along the length and around the circumference. For the ant, the circular direction is real, but bounded. If it walks far enough in that direction, it returns to where it started. If extra dimensions are curved up like that, on scales far smaller than atoms, you would not notice them in your daily life. You would be like someone walking along the hose at a distance, unaware of the minute circle hidden in each point. Only at very high energies, probing very small distances, might the extra directions become active in ways we could detect. So far, our experiments have not reached a regime where such effects are clearly visible. The shapes used to curl up these dimensions are not simple circles. They can be intricate, with many folds and holes. One class of shapes used in string theory goes by the name of Calabi-Yau manifolds. You can think of them, very loosely, as multi-dimensional surfaces twisted and connected in complex ways, like a sculpture made of tunnels and cavities. The precise shape matters, because it influences the kinds of vibrational patterns the strings can have, and therefore the kinds of particles and forces that appear in the lower dimensional world we perceive. Change the curled geometry, and you change the apparent physics. This gives a new meaning to the idea of a door in space. A door, in our usual picture, connects one region of 3-dimensional space to another. You step forward, and you are in a different room, but a door that opens along a compact extra dimension would not take you somewhere else in the familiar sense. It would move you sideways into a direction that is not part of your everyday vocabulary. To a 3-dimensional observer, like you, such a movement might look like teleportation. One moment you are here, the next moment you are somewhere else. with no path in between that makes sense inside the ordinary three axes. In principle, if higher dimensions are real, particles could sometimes take shortcuts through them. Two points that are far apart in three-dimensional space might be close together when measured in the full higher dimensional geometry. A path that seems long and winding in your space could correspond to a straight line if you are allowed to move sideways in one of the hidden directions. This is the intuition behind some ideas of wormholes and shortcuts in space-time, though the exact mathematics is subtle and still under debate. From a simulation perspective, higher dimensions begin to look like system layers. In a computer program, what you see on the screen is rarely the full story. There are hidden tables, data structures, and control flows that you do not interact with directly. Yet they shape everything that appears. A character walking across the screen moves in two visible dimensions, but their position is stored as entries in a multidimensional state space that includes variables you never see. When you encounter a glitch, you are not watching the screen misbehave in isolation. You are seeing a moment where the hidden layers failed to sync with the visible layer. If our universe contains extra dimensions that are usually hidden, then an anomaly in their structure might occasionally bleed into the visible three, creating local effects that feel impossible according to our surface-level rules. A particle that should not be able to cross a barrier might find a path through the curled dimensions. A region of space might have slightly different properties because the compact geometry is shaped differently there. These are tiny effects, far beyond what you notice when you drop a mug or misplace your keys. But they suggest a pattern. The visible world could be a slice through a deeper structure that has more directions than you can experience directly. The language of brains adds another layer to this picture. In many higher dimensional theories, our entire observable universe can be thought of as a three-dimensional membrane, or three-brain, embedded in a higher dimensional bulk. You can imagine it as a thin sheet floating in a larger space with more dimensions. Particles corresponding to familiar matter and forces might be confined to this sheet, while other kinds of fields, including gravity, might extend into the bulk. If there are other brans parallel to ours in that bulk, they would be like neighboring universes, incredibly close in the full higher dimensional sense, but completely out of reach along the directions we can move. In some speculative models, a gentle collision between brains could even trigger something like a Big Bang, heating up the affected brains and creating conditions for a universe like ours to emerge. These ideas are not established facts. They are attempts to stretch our mathematical tools to describe how a universe could begin. What matters for our story is how casually they treat the idea that the world might have more directions than those that fit into human intuition. For most of your life, none of this changes how you walk, breathe, or love. You still navigate rooms with three spatial axes. You still age along a single time axis that moves from earlier to later and never backward. But in the background, the picture is less tidy. Space could be layered. The basic constituents of matter could be oscillations in extended objects that need more dimensions to vibrate in. What you call emptiness could be threaded with hidden directions, curled too tightly for your senses to explore. This has a quiet psychological effect. It suggests that when you think of yourself as a person in space, you are already using a simplified map. You are not simply located at a point in three dimensions. You are part of a configuration in a higher dimensional structure you will never fully see. Your body, your brain, your memories. All of them are patterns in fields that extend into directions that are, for practical purposes, permanently off limits. You can live an entire life without caring about that. But if you do pause to think about it, the feeling is odd. You are local in ways you can sense, and spread out in ways you cannot. If doors can open sideways instead of forward, then the idea of inside and outside starts to blur. Each of your experiences is local, personal, bound to a perspective. The underlying structure that supports those experiences might be global, multi-layered, indifferent to the way you carve it up into rooms and streets and skies. You fall in love in one apartment, fear death in one bed, ask questions into one night. All the while, the deeper architecture of reality may be folding and twisting through directions you have no language for. And somewhere in that gap between the smallness of your point of view and the size of the stage, the suspicion grows that what you call reality might be less a solid block and more a cross-section through a space that does not care how many dimensions you find comfortable. If what you can see is only a slice through a space that does not care about your preferences, then there is no obvious reason why the slice has to look like this. The familiar sky could be just one way for a universe to be, not the default, not the optimum. Just one arrangement among many that never learned how to be otherwise. When physicists talk about the laws of nature, it is easy to hear something rigid and absolute. Equations written once and for all, numbers fixed by some deep necessity. But if you look closer, many of those equations contain parameters that could, in principle, have taken different values. A parameter is simply a number you put into a formula that changes how it behaves. The way changing the tension of a guitar string changes the sound, while the basic rules of vibration stay the same. In our universe, these parameters control the strength of gravity, the masses of particles, the intensity of forces, the rate at which space expands. Change them even slightly, and the world can become unrecognizable. It is not hard to imagine a universe where gravity is weaker than it is here. Gravity is the attraction between masses, the pull that keeps planets in orbit and your feet on the floor. In our cosmos, that pull is incredibly feeble compared to other forces. You can lift a metal paperclip with a small magnet against the entire mass of the Earth. But feeble does not mean arbitrary. In many models, if you weaken gravity further, stars struggle to form. The gas in young galaxies does not collapse easily enough to ignite nuclear fusion. Instead of long-lived stars with stable warmth, you might get a thin mist of matter, spread out and cold, never quite settling into the luminous points you see when you look up on a clear night. Imagine such a universe. Call it, for convenience, Universum Proximum, the neighboring universe. From the outside, if such an outside existed, it would be made from the same basic ingredients as ours, but with the gravitational attraction tuned just a little lower. In this world, galaxies would be ghostly, their shapes loose and fragile. The few stars that manage to form might be scattered and short-lived, flickering into existence and fading before they can host anything like a stable planetary system. On the scales that matter for chemistry and life, the consequences would be brutal. Planets like Earth form from disks of dust and rock circling young stars. They require a delicate balance between gravity, which pulls material together, and other processes that break clumps apart. If gravity is too weak, those clumps never grow large enough. You might get small, irregular bodies, more like rubble piles than planets, wandering in space without strong atmospheres, without stable climates, without oceans. There would be no long-term surfaces for liquid water to pool, no thick blankets of air to circulate heat, no continents to erode into fertile soil. There is a word in physics for how sensitive the emergence of complex structures can be to parameter choices. It is fine-tuning. The idea is simple. When you vary the values of certain constants in a mathematical model, you often find that large regions of the possible range lead to universes that are dull in a very specific sense. No chemistry, no stable atoms, no long-lived stars. Nothing that can store and process information in rich ways. Only narrow bands of values produce environments where complexity can grow. Our universe seems to lie in one of those narrow bands. You could tell this story in many tones. You could hear it as evidence that the universe was designed with care. You could hear it as support for a multiverse where many sets of parameters are tried. And we naturally find ourselves in one of the rare combinations that allow observers. You could also hear it, more quietly, as a reminder that the features you rely on to orient yourself, the solidity of matter, the warmth of the sun, the relative calm of physical law, are not generic. They are local conditions in a much larger landscape of ways reality could have failed to make room for you. The phrase, worlds that should not exist, does not mean universes that are logically impossible. It means universes that feel wrong to your intuition, because they lack the elements you associate with existence itself. A cosmos without stable atoms may seem like no cosmos at all. A cosmos where time behaves in ways that never allow anything persistent to emerge may feel like an empty idea. But from a neutral physical standpoint, these are just points in parameter space, coordinates in a high-dimensional chart of possible rule sets. Some of those points describe universes that begin hot and dense and then rush apart so quickly that matter never clumps. Others describe universes that collapse back into themselves before they have time to cool. Some yield only black holes and radiation. Others only diffuse fields without local structure. These are not fantasy in the sense of breaking the mathematics. They are what you get when you allow the same basic equations to play with different settings. When you picture beings from another universe, it is tempting to imagine them as variations on yourself. Perhaps taller or smaller, perhaps made of different elements, but still walking, thinking, wanting in ways you can recognize. That may be a deep failure of imagination. In many branches of the possible, there simply is no space for organisms built from cells and carbon and water. If something like life exists at all, it might be a pattern in electromagnetic fields, or a kind of self-organizing turbulence in a plasma, or a structure in a condensed matter system with properties we do not yet know how to describe. Its sense of distance, duration, and identity could be so alien that your words for self and world no longer apply. The more we learn about our own universe, the more room we find for such strangeness even within it. Neutron stars, for example, are objects left behind when massive stars explode. They pack more mass than the sun into a region about the size of a city. Their matter is so compressed that atoms collapse, and protons and electrons merge into neutrons. A teaspoon of that material would weigh as much as a mountain. On their surfaces, gravity is so intense that if you stood there assuming you could, you would be crushed instantly. Yet, even these extremes are modest compared to what might exist in universes with different parameters, where matter could form phases unknown to our physics, with properties we have no metaphors for. We often comfort ourselves with the belief that if something exists, it must exist for a reason. That the universe, in some sense, wanted life, or at least did not mind producing it. But when you see how difficult it can be to get even basic structures like stars and planets out of the equations, another picture suggests itself. Perhaps our universe is one of the worlds that should not exist, in the sense that the default behavior of the laws would have been to make something simpler, harsher, less hospitable to meaning. Perhaps the fact that there are hands to write equations and eyes to read them is less like a natural outcome and more like a rare side effect. This does not lead to a clear moral. It does not tell you that your life is precious in a cosmic sense, or that it is an accident, or that you are obligated to feel grateful. It only sharpens a contrast. On one side, a vast space of possible rule sets, most of which yield barren or sterile worlds. On the other, the very specific set of rules you woke up inside, which happens to allow galaxies, chemistry, biology, and late-night thoughts about reality from within your own story. It is easy to treat that as normal. From a slightly wider view, it begins to look almost unreasonable. If you import this into the simulation question, The effect is strangely doubled. A simulation does not have to explore every possible universe. It only has to implement one consistent set of rules. But if whoever or whatever built it had access to the larger space of options, then our world might sit on a boundary between many non-viable designs. Perhaps the underlying system tried many configurations before settling on this one. Perhaps it did not care at all. And this is what you get when you roll mathematical dice often enough. Or perhaps these are human projections. Attempts to treat the space of possible laws as a drama with motives and goals. Either way, the exercise leaves you standing in the same place, looking at the same sky, with the same limited lifespan, only now. The ground beneath your feet feels more conditional. You are not embedded in the universe, as if there could not have been others. You are living inside one specific world that could easily have fallen on the wrong side of the line, one of the worlds that, from your narrow perspective, should not exist at all. If this world already feels improbable, it is worth asking what happens when you step sideways, not into another universe, but onto other worlds that share our same basic laws and still look like mistakes. Astronomers use a simple word for those worlds: exoplanets. It just means planets that orbit stars other than the Sun. The way we find them is almost disappointingly indirect. We watch starlight dip as a planet passes in front, or wobble as a planet's gravity tugs the star back and forth. From those tiny changes, from those almost flat lines of light, we reconstruct entire landscapes, temperatures, atmospheres, orbits, and the more of them we find, the more our own Earth starts to look like an unusually gentle setting in a catalogue full of hostile options. Take the class of planets called hot Jupiters. The name sounds playful. The reality is not. These are gas giants, roughly similar in mass to Jupiter, but orbiting so close to their stars that they complete a year in just a few days. Imagine a world parked closer to its sun than Mercury is to ours. Its day side is heated until molecules come apart. Its atmosphere is whipped into supersonic winds, circling the planet from hot to cold, dragging clouds of vaporized rock with them. On at least one such planet, analysis of the light that filters through the atmosphere suggests the presence of tiny glass particles in the air. If you could stand there, which you cannot, you might find yourself in horizontal glass rain. Shards carried on winds of thousands of kilometers per hour. The sky glowing a sickly blue. That image alone feels like a rendering error. It sounds like someone chose the wrong value in a weather engine. Glass instead of water. Supersonic winds instead of a breeze. But it is simply what you get when the same physics that makes our gentle storms is pushed into a much more extreme configuration. Temperature high enough, gravity strong enough, distance to the star small enough. No new magic, just a different point in parameter space. Other worlds are dark in a way that breaks intuition. There is a known planet that reflects less light than charcoal. It orbits so close to its star that its atmosphere is heated, until clouds of vaporized metals and complex molecules form. Those clouds absorb almost all the starlight that hits them. If you looked at that planet from space, you would not see a bright crescent like you do with Venus. You would see a hole, a moving absence, like a section of the sky where someone turned the brightness down to almost zero. Calling it a planet feels wrong, as if reality accidentally spawned a moving patch of night. Then, there are the so-called lava worlds. These are rocky planets that orbit their stars in such tight loops that their surfaces are molten on at least one side. Instead of having continents and oceans, they may have vast seas of lava, with rock vapor in the air and mineral clouds that condense and rain back down as droplets of molten stone. Their day sides glow faintly red, not from cities or fires, but from the entire ground simmering just below the point of boiling. On the night side, those seas may cool into crusts that crack and refreeze as molten material circulates underneath. A coastline there would not be a stable border between land and sea. It would be a flickering fringe between solid rock and liquid rock, shifting with the local weather of magma. Some planetary interiors are stranger than their surfaces. Deep inside Uranus and Neptune, under enormous pressures, experiments and calculations suggest that methane and other carbon-rich compounds might split into hydrogen and diamond. Those diamonds would then sink, forming a kind of diamond rain, not a romantic shower of cut gemstones, but a slow, crushing drift of crystalline carbon through layers of exotic ice and fluid. It is a mundane consequence of chemistry at high pressure. It also sounds like a piece of digital concept art for a game that wanted to be a little too clever. Once you accept that planets can do these things without breaking any rules, you can push the possibilities further. Gas giants can orbit dead stars. Rocky planets can circle pulsars, which are spinning neutron stars with beams of radiation sweeping through space like lighthouse beams. Any surface there would be bathed in intense bursts of high-energy particles. In a rhythm tied to the star's rotation, day and night would not be simple cycles of light and dark. They would be patterns of radiation pulses, ticking out an inhuman time. Even within our own solar system, the variety is uncomfortable. Jupiter's moon Io is covered in sulfur volcanoes, its surface constantly resurfaced by eruptions driven by tidal forces. Saturn's moon Titan has lakes of liquid methane and ethane, hydrocarbons that are gases on Earth but behave like water there, forming rivers, rain, and seas under a hazy orange sky. The moon Enceladus, smaller than many countries, has geysers that shoot plumes of water ice into space from a subsurface ocean, creating a thin, shimmering ring around Saturn. None of these require new physics. They just explore the edges of what the old physics can do. If you were dropped anywhere on those worlds with your current body, you would die almost instantly, in a variety of ways: crushed, frozen, boiled, suffocated, irradiated. Their beauty is crucially indifferent to your existence. The auroras on a hot Jupiter, the glint of diamond deep inside an ice giant, the mirror calm of a methane lake under an alien sky, none of it is about you. None of it needs you to watch. And yet, through telescopes and instruments, you see them anyway, as if peaking at levels of a simulation you were never meant to load. The phrase rendering error comes from computer graphics. It describes what happens when the system that turns a model into an image fails in some way. Textures do not align. Shadows fall in impossible directions. Objects flicker, stretch, or clip through each other. You know, when you see it, that something underneath went wrong. There is a mismatch between the rules you expect the engine to follow and what appears on the screen. Looking at some exoplanets, it is tempting to borrow that metaphor. Skies raining glass, seas of molten rock, worlds darker than coal. From the perspective of creatures who evolved under a yellow sun, with liquid water oceans and an oxygen-rich atmosphere, these things look like bugs, not features. The sensible part of your mind knows better. The equations say they are fine, but the intuitive part sees a glitch. This tension is useful. It shows how provincial your instincts really are. If our own world is one small, habitable niche in a space of possibilities that includes these extremes, then the idea that reality should look natural or smooth is revealed as a local bias, not a property of the universe itself. The universe does not care if a landscape looks like it belongs in a documentary or in a surrealist painting. It only cares, in a manner of speaking, that the underlying rules are followed. If you bring the simulation question back in here, it does not give you an answer, but it does sharpen the edge of the question. If someone showed you a virtual world with glass rain, black planets, and diamond storms, you would praise their imagination. You might complain that it feels over-designed, that no real universe would be that baroque. Yet this is the universe you already live in. You are the one who looks simple by comparison. A thin layer of biology on one modest rock, trying to decide which version of impossible you are willing to call real. In a universe that already feels like it is pushing its own rules to the edge, it is hard not to ask a very simple, very human question. Is there a shortcut? Not an emotional one, not a philosophical one, but a literal path that bends distance into something smaller than it appears. In our current best picture of gravity, the shortcut does not begin with tunnels or portals. It begins with a change in how we think about space and time themselves. Albert Einstein's general theory of relativity does something quietly radical. It treats gravity not as an invisible force pulling on objects, but as the curvature of space-time. Space-time is the combined fabric of where and when, a four-dimensional structure in which events have both positions and times. Massive objects, like stars and planets, curve this fabric. Other objects follow the curves. What you feel as the pull of gravity is just your body following the shortest available path through a geometry you cannot see. A common way to picture this is with a rubber sheet. Place a heavy ball in the middle and the sheet dips. Roll a smaller ball nearby and it spirals inward. Not because the large ball is pulling directly, but because the sheet is curved. This image is not perfect, because it uses gravity in the downward direction to explain gravity itself. But it helps with one key point. If you can change the shape of space-time, you can change what counts as a straight line between 2 points. A wormhole is, in essence, a particular way of bending that geometry. Instead of thinking of space as a smooth, gently curved sheet, imagine that you take 2 distant points and pinch them together, creating a bridge between them. On a flat map, 2 cities might be far apart. But if you fold the map so that the cities touch, then a tunnel that cuts through the fold would be much shorter than the path you would draw on the unfolded surface. A wormhole is the space-time equivalent of that fold and tunnel. It connects 2 regions that would otherwise be separated by vast distances, potentially even different universes, through a short passage outside the usual routes. The mathematics of general relativity allows such structures. Solutions to the equations exist in which space-time forms a bridge between 2 regions. The earliest versions, sometimes called Einstein-Rosen bridges, arise when you look at the idealized description of a non-rotating black hole. In that case, the geometry includes a connection between 2 asymptotically flat regions, often interpreted as 2 universes or 2 parts of one universe. From the standpoint of the equations, it is a wormhole. But there is a catch. That particular bridge is not traversable. It pinches off too quickly. Anything that tries to cross from one side to the other is crushed and trapped behind an event horizon. An event horizon is a boundary beyond which events cannot influence an outside observer. Once you cross it, all paths into the future lead deeper into the black hole. The Einstein-Rosen bridge exists as a geometric curiosity, but it does not offer a usable door. Later work explored whether other types of wormholes could avoid this fate. The key requirement for a traversable wormhole is that the throat, the narrow region connecting the mouths, must stay open long enough for something to pass through. When physicists analyze what kind of matter or energy would be needed to hold such a throat open, they find something very strange. It appears to require exotic matter. Exotic here does not mean mystical. It means matter or fields with properties that violate certain energy conditions that ordinary substances satisfy. In particular, the wormhole seems to need negative energy density in some region. Negative energy density, in this context, is not just having less energy than usual. It is having a local configuration where the energy is below that of empty space. Quantum field theory, which describes particles as excitations of underlying fields, does allow temporary negative energy densities in small regions as long as they are balanced by positive energy elsewhere. The Casimir effect, for example, involves two uncharged metal plates placed very close together in a vacuum. Because of the way quantum fluctuations are restricted between the plates compared to outside, the configuration behaves as if there is a small region of negative energy density between them, leading to a tiny, attractive force. This is a real, measured effect. However, the negative energy produced in such experiments is incredibly small and localized. There is no known way to scale it up to the level required to stabilize a macroscopic wormhole throat. The theoretical results suggest that, in principle, if you had enough negative energy arranged in the right way, you could engineer a traversable wormhole. In practice, our current understanding of physics gives no hint that such engineering is physically achievable. The universe, as far as we can tell, does not hand out ready-made doors. Still, the concept persists, because it illuminates how flexible space-time can be in theory. If you write down the equations and ask not what does nature do by habit, but what does the geometry allow, you find a surprisingly large room for structures that behave like shortcuts. Some solutions describe wormholes connecting distant regions of the same universe. Others describe connections between different universes embedded in a larger multiverse. Some even flirt with constructions that might allow time travel, with all the paradoxes that suggests, though most of those scenarios run into stability problems or violations of basic assumptions. It is tempting, again, to translate this into narrative terms. A wormhole feels like an escape mechanic. The universe is large. Distances are crushing. The speed of light is a hard limit. And yet, just beneath the surface, the equations hint at a way around it. If only you could find or build one of these structures, you could step from star to star, like crossing a room. From the perspective of a possible simulation, wormholes have an even more provocative flavor. Many virtual worlds use something like portals to manage space efficiently. Instead of simulating every region all the time, the system focuses resources on the areas where active characters are, and uses shortcuts in the underlying data structure to connect distant locations. Walk through a door, and the system unloads one region and loads another. To the character, it feels like teleportation. To the code, it is just a change of pointers. In that language, a wormhole would look like an exposed part of the system's internal wiring. Not a bug, but a feature that reveals how space is stitched together. A door that does not just move you within the world, but briefly takes you along a path that only the underlying architecture was supposed to use. We are firmly in metaphor here. There is no evidence that our universe handles memory or resources the way a human-designed game engine does. But the resonance is hard to ignore, especially when our own mathematics, independent of any simulation story, produces objects that behave so much like hidden connections. There is another way in which wormholes press on our intuitions. They challenge the idea that distance is a simple, objective thing. We are used to thinking that the shortest route between 2 points is a straight line in space. General relativity replaces that with the notion of a geodesic, the shortest path in curved space-time. A wormhole simply exploits a different part of that geometry. 2 points that are far apart in the 3 coordinates you are familiar with could be close in the full 4-dimensional structure, if the geometry is folded appropriately. In that sense, a wormhole does not cheat. It obeys the rules of the metric, the function that defines distances in space-time. It just uses a part of the rulebook you rarely think about. Even without physical wormholes, the idea that distance is not absolute has real consequences. Light from distant galaxies takes time to reach us, and during that time the universe expands. The path that light follows is not a straight line in an unchanging stage. It is a curve through a dynamic geometry. On large scales, space itself stretches, changing what it means to talk about how far away something is. When cosmologists say that a galaxy is a certain number of light-years away, they have to specify whether they mean the distance now, the distance when the light was emitted, or some other definition tied to the expansion history. Distance is already less straightforward than your day-to-day experience suggests. So when wormholes slip into the conversation, they are not adding a completely alien idea. They are extending a trend. The more carefully we look at space-time, the less it behaves like a rigid stage, and the more it behaves like a flexible, dynamic structure that can, at least in the equations, be bent into forms that would once have been filed under fantasy. Will we ever see a wormhole? Probably not. In the dramatic. Walk through a glowing tunnel sense. If they exist naturally, they might be microscopic and unstable. If they can be engineered, it would require control over energy and matter far beyond anything we can currently imagine. The universe may simply never offer us that option. And yet, the mere fact that the equations allow such doors changes how you think about confinement. You live in a cosmos where distances are enormous, lifespans are short, and the speed of light is a ceiling you cannot break. That already places you in a kind of prison of scale. Wormholes are like drawings of keys on the walls of that prison. They may not exist in the actual stone. They may only exist in the blueprints. But knowing that the blueprint includes them is enough to remind you that your sense of what is necessary, what is inevitable, is once again tied to a limited view. You still have to wake up tomorrow in the same body, on the same planet, moving through the same slow, local space. Nothing in this reshapes your responsibilities or answers the question of how to live. What it does, quietly, is loosen your grip on the idea that the structure around you is simple. It suggests that if this is a cage, it is not a cage made of straight lines. It is something curved and folded, with theoretical doors drawn into the geometry. Doors that you may never touch, but that nonetheless haunt the way you picture the world you are trapped in. If the blueprint of the universe quietly admits doors it never builds, then black holes are where it stops pretending those doors would be safe. They are the places where the rules we trust most walk right up to the edge of a cliff and keep going anyway. A black hole begins with something surprisingly ordinary, a star that runs out of fuel. For most of its life, a star is a balancing act. On one side, gravity pulls its matter inward. On the other, nuclear reactions in its core push outward, as light and hot particles stream through its layers and into space. As long as those reactions continue, the star holds itself up. When the fuel is exhausted, that outward push fades. Gravity wins. If the star is small enough, the collapse stops at a dense object like a white dwarf or a neutron star. Those are already extreme. In a white dwarf, matter is packed so tightly that a spoonful would weigh as much as a mountain. In a neutron star, that same spoonful would weigh more than many mountains combined. But there is still a surface, still a place where you can, in principle, stand and say, here is the star, and here is space around it. If the collapsing core is more massive than a certain critical limit, even those structures cannot resist. The inward crush continues, and there is no known force in ordinary physics that can stop it. Space-time itself curves so steeply that escape becomes impossible. Not difficult, not unlikely, impossible. Anything that crosses a certain boundary around the collapsed region is trapped forever. That boundary is called the event horizon. An event is just something that happens at some place and time. The horizon is the surface beyond which no event can send a signal to the outside world. From far away, a black hole is defined almost entirely by a few simple properties: its mass, its spin, and its electric charge. There is a famous slogan in the field that says black holes have no hair. It means that, apart from those basic properties, all the details of what fell in are erased from the outside description. Whether the black hole formed from a star, a cloud of gas, or a library of books. The end result is the same: a region of space where gravity is so strong that even light cannot climb out. The inner structure is more mysterious. If you follow the equations of general relativity inside the event horizon, you find that the collapse of matter continues toward a point of infinite density and curvature called a singularity. A singularity is a place where the theory stops giving sensible answers. Not necessarily a literal point in space, where everything is crammed. It is a signal that the current description is incomplete. At that point, our best map of reality simply tears. Around many black holes, matter does not fall straight in. It spirals, forming a whirlpool of gas and dust called an accretion disk. As material in that disk rubs against itself, it heats up to tremendous temperatures and emits light, often in X-rays and other high-energy forms that our eyes cannot see. In some systems, powerful jets of particles shoot out along the rotation axis of the black hole, extending far into space. Taken together, these structures turn black holes into some of the brightest objects in the universe. The region itself is dark, but the violence of what happens just outside the event horizon lights up the cosmos. For a long time, black holes were theoretical creatures. The equations allowed them, and indirect evidence suggested they existed, but no one had seen their silhouette. That changed when an international collaboration used a network of radio telescopes spread across Earth to create a planet-sized instrument. By carefully combining signals from observatories separated by entire continents, they were able to resolve the region around the giant black hole at the center of a distant galaxy. The resulting image, shared publicly in the year, often written as 2019, showed a glowing ring of emission surrounding a dark central shadow. The shadow is not the black hole itself, but the region where light paths are bent so strongly that they miss our line of sight. It was the first time we had, in any sense, seen the outline of an event horizon. That picture had an odd emotional effect on many people. On one level, it was technical and expected. Simulations based on general relativity had predicted a similar ring. On another level, it felt like looking at the face of something mythic. Human cultures have told stories about devouring voids for as long as stories have been told. Here, finally, was a real one, rendered not by a painter but by the sky and our instruments. A hole in the visible, outlined by light that almost escaped and did not. Whenever we reach the edge of knowledge, myths begin. Black holes have attracted their share. They are said to be portals to other universes, time machines, gateways to higher dimensions. Some of these images are inspired by genuine features of the equations. Near an event horizon, time dilation becomes extreme. Time dilation is the slowing of time in a strong gravitational field compared to a weaker one. A clock falling toward a black hole appears to tick more and more slowly as seen from far away, approaching a standstill as it nears the horizon. Light climbing out is stretched to longer wavelengths, its energy drained by the climb. These effects are real and have been confirmed in milder forms near Earth and in the orbits of stars around our own galaxy's central black hole. But the leap from time stretching and strong gravity to full-fledged portals is where mathematics ends and speculation begins. There are solutions to the equations of general relativity that describe rotating black holes with internal structures that include regions resembling wormholes. However, most analyses suggest that those structures would be unstable under realistic conditions. Small disturbances would cause them to pinch off or become singular. In other words, even if the equations admit bridges and tunnels inside idealized black holes, nature may not build them in a way that allows safe passage. The truly disturbing questions arise not from travel fantasies, but from information. In quantum theory, there is a principle that information is never destroyed. Information here does not mean gossip or news. It means the full set of physical details that specify the state of a system. You can scramble information, hide it, spread it out, But the underlying theory says that if you could reverse the process perfectly, you would get back what you started with. Processes are reversible at the deepest level, even if they are effectively irreversible in practice. Black holes seem to violate this. Throw something into a black hole, and from the outside, all that appears to matter is the total mass, spin, and charge you added. Drop in a book, a planet, a person, and a beam of light, and you get the same black hole described by the same few numbers. When the black hole later evaporates by emitting faint radiation, a process predicted by Stephen Hawking, and now called Hawking radiation. That radiation appears to be almost perfectly thermal. Thermal radiation is like the glow from a hot object, carrying information only about the temperature, not about the precise structure of what produced it. If that is the whole story, then detailed information about what fell in is gone forever. This is the black hole information paradox. It is the clash between the demands of quantum theory and the behavior of black holes as described by general relativity. Over decades, many ideas have been proposed to resolve it. Perhaps information is encoded in subtle correlations in the outgoing radiation. Perhaps the interior and exterior descriptions of the black hole are related in a way that prevents double counting. Perhaps our understanding of space-time breaks down at the horizon in ways we do not yet grasp. None of these proposals has been elevated to the status of accepted fact. The paradox remains a live research topic. What matters for our purposes is not to pick a winner among those ideas. It is to notice what their existence reveals. Black holes are not just astrophysical curiosities. They are places where our two most successful theories of nature give conflicting answers about what happens. They mark a boundary in our understanding beyond which we currently cannot see. When you approach that boundary with mathematics, you find symbols that refuse to cooperate. When you approach it with imagination, you find myths. From a certain angle, a black hole looks uncomfortably like a system boundary in a simulation. There is an inside, cut off from the outside. Information goes in and does not come back in any recognizable form. The internal workings are hidden from observers on the outside. You can describe the boundary itself with increasing precision, but you cannot directly inspect what lies beyond it. The analogy is just that, an analogy. Real black holes emerge from continuous equations, not from lines of code, but they create a similar psychological effect. They say there are places in this universe where your usual tools for making sense of things simply stop working. You will never fall into a black hole. The nearest known ones are unimaginably far away in human terms, and your life is short. Your fears and hopes will be resolved long before gravity has a chance to pull you across an event horizon. Still, the existence of these objects reaches into your thoughts. They tell you that the universe contains regions where questions like, what is inside, may have no clear answer according to the theories we have now. They embody the idea that reality can be locally opaque, not just practically, but in principle. You can live your entire life without thinking about that. You can treat black holes as distant monsters, useful for dramatic posters and special effects, or you can let them do what they really do best, remind you that the frameworks you use to feel at home in the universe are partial. They work astonishingly well in many regimes. They give you smartphones and spacecraft and medical imaging, and yet, at the edge of a black hole, they argue with each other and fall silent. In that silence, you are left with a fact that is easy to state and hard to absorb. There are places in the universe that you can write equations about, build telescopes to observe, and still not truly understand. Places where physics as you know it breaks. And stories rush in to fill the gap. Whether or not those stories include simulations and hidden codes, the gap itself is real. It is one more sign that whatever reality is, it is not yet something you can claim to see from the outside. Even if you never stand at the edge of a black hole, you still live with a quieter kind of event horizon. It is not a circle in the sky. It is the simple fact that almost everything in the universe is too far away for you to ever touch. When we talk about stars, we usually reach for comforting metaphors, constellations, stories, guides for navigation. It is easy to forget that each point of light is not up there in a vague way, but at a very specific distance that your body will never cross. The nearest star beyond the Sun is a little over 4 light years away. A light year sounds poetic, but it is just a unit of distance, the span that light covers in 1 year of travel, moving at about 300,000 kilometers every second. Multiply that speed by all the seconds in a year, and you get a number so large it stops meaning anything. Then imagine that distance, repeated 4 times, just to reach the closest neighboring sun. With current rocketry, built on chemical fuel that pushes exhaust out the back and carries all of its propellant on board, that journey would take tens of thousands of years. Not metaphorical thousands. Actual generations stacked on generations. Entire languages shifting, cultures dissolving and reforming, while a thin metal shell drifts between the stars. No one who begins the trip would see its end. The ship would arrive, carrying descendants of descendants, people whose ancestors made a promise on their behalf long before they were born. This is what interstellar distance really does. It turns travel into inheritance. It converts a simple desire go there into a chain of obligations that stretches beyond a single life. That is why, in serious discussions, the phrase generational ship appears. A generational ship is a vessel designed not for one crew, but for many. It is a small world intended to be self-sustaining over centuries, with its own closed ecosystems, its own social structures, its own myths. The people on board would be born inside a project they did not choose. For them, the destination would be a story, not a memory. The physics that creates this prison wall is simple. In the vacuum of space, there is no air to push against. So your engine must fling mass out at high speed in the opposite direction to move forward. This is the rocket principle. The faster you want to go, the more propellant you need. But the more propellant you carry, the heavier you are. And the more propellant you need just to accelerate the propellant. This feedback loop culminates in what engineers call the rocket equation. You do not need the algebra. You only need the consequence. With chemical fuels, you hit diminishing returns very quickly. You can escape your planet. You can cross your solar system in years. Crossing the gap between stars is another story. People have imagined more exotic options. Antimatter propulsion appears often in that list. Antimatter is a form of matter where properties like electric charge are reversed. When a particle meets its antimatter twin, they annihilate in a burst of energy. In principle, this process is far more energy-dense than chemical reactions. A spaceship that could use antimatter efficiently might reach a significant fraction of light speed, enough to reduce a centuries-long trip to decades. But in practice, producing and storing antimatter is beyond our capabilities. We can create tiny amounts in particle accelerators, microscopic flashes that vanish almost instantly when they meet ordinary matter. Turning that into a fuel tank is as distant as the stars themselves. Another idea is the solar sail, or more generally, a light sail. The concept is elegantly simple. Light carries momentum, even though it has no mass. If you stretch a large, reflective sheet in space, photons from a star or from powerful lasers can push on it, very gently. Over time, that continuous push can accelerate a craft to high speeds without carrying fuel. The challenge is building a sail that is light and strong enough, and providing a sustained, intense beam of light to drive it. Experiments with small sails have already begun in near-Earth space. The dream is to scale that up, to send wafer-thin probes racing toward nearby stars, arriving within a human lifetime. Even then, these would not be crewed ships. They would be cameras on needles, flung outward to send back compressed glimpses. However you approach it, the pattern returns. Distance is not just a number on a map. It reshapes what it means to explore. Within a solar system, exploration can be an extension of human presence. Vehicles can be piloted in real time, or at least with short delays. Strategies can be adjusted. Rescue is at least conceivable. Beyond that, exploration becomes more like sending messages in bottles into a dark ocean, knowing you will die long before anyone reads what they contain. From an existential angle, the effect is subtle but real. You grow up with stories of the galaxy as a playground. Starships, with artificial gravity and clean windows. Fleets assembling, departing, returning. It is an appealing image because it takes the scale of the cosmos and shrinks it to the scale of a sea or a continent. Something you can cross, something your species can claim. The cold fact is that the speed of light is finite, and so are your lives. The combination turns the galaxy into a set of lights you can see but never visit in person. Not with flesh and blood and ordinary time. There are proposals that press harder on the limits. Nuclear pulse propulsion imagines detonating a series of nuclear devices behind a spacecraft, each blast pushing it forward, like a stone skipped across the surface of a pond by repeated hits. Fusion drives would harness the same reactions that power stars, fusing light nuclei to release vast amounts of energy. Both approaches could, in principle, reach higher speeds than chemical rockets. Both face immense engineering challenges, ethical questions, and unknowns about what decades in such conditions would do to a crew. Then there is the psychological dimension, which is harder to quantify. Even if you solved the propulsion problem, you would still be sending human minds, designed by evolution for small groups and short horizons, into isolated tubes for decades. How do you keep meaning alive in such a space? How do you prevent cultures on generational ships from fracturing, stagnating, or drifting into patterns that no longer care about the original mission? At what point does the voyage stop being about the destination and become an experiment in building societies in exile? The question echoes beyond engineering. It touches on how you relate to your own limits. You live your entire life confined to one planet, circling one star, in one arm of one galaxy. You will never walk under another sun. You will never look up at a night sky where the constellations are entirely different, except in images. The prison wall of distance is not just out there, between stars. It is here, in the finite span of your days. For some, that confinement breeds a sense of insignificance. If the universe is so large and you are so local, what can anything you do matter? For others, it has the opposite effect. The fact that you are confined sharpens the value of what happens inside the walls. If your whole life must be lived within one set of skies, that makes the way you move under those skies more, not less, important. The unreachable stars become a backdrop against which your choices stand out. If you look at this through the lens of the simulation question, distance begins to feel like design. In many digital worlds, the player's movement is constrained. Borders are disguised as mountains, as oceans, as energy fields. You can see landscapes painted in the distance that you can never actually reach, because the system does not simulate them at full detail. They exist as scenery, not as places. In our universe, interstellar space risks feeling like that. You can calculate the paths, write trajectories, name exoplanets, map galaxies. But for you, personally, they function more as a rendered background than as accessible terrain. Of course, unlike a game, there is no evidence that anyone deliberately set those limits. The speed of light and the scale of the cosmos may simply be what you get when these laws of physics unfold. Still, the resemblance is there in the emotional texture. You are given a world rich enough to raise questions about what lies beyond, and a body too short-lived to ever check. You are encouraged to imagine and constrained from verifying. In the end, interstellar travel is less about rockets and more about acknowledging that you inhabit a reality with hard edges. Some of those edges are physical, some are temporal, some are built into the way your mind works. The stars invite you and forbid you at the same time. They shine into your nights as if to say, there is more. And then, quietly, they add, but not for you. If you cannot cross the great distances by moving through space, the next temptation is simple. Maybe you do not have to. Maybe the way out is not across. But along the other axis, you usually treat as fixed. We live with two kinds of time. There is the time of clocks and calendars, the steady tick that lets you make appointments and remember birthdays. And there is the time you feel, the subjective flow that speeds up when you are happy, stretches when you are bored, freezes when something terrible happens. For most of your life, you assume these two are tied together. The minute hand moves, your heart beats. Events line up in a single order. Past, present, future. A sequence that cannot be rearranged. Physics complicates this. In the framework of relativity, time is not a separate river. It is woven together with space into a four-dimensional fabric called space-time. An event is something that happens at some location and some moment. To specify it, you need 3 spatial coordinates and 1 temporal coordinate. Change your state of motion, and the way you slice that fabric into space and time changes. Different observers, moving differently, can disagree about how far apart 2 events are in space and in time, even while agreeing about the deeper structure underneath. One of the simplest and strangest consequences of this is time dilation. Time dilation means that the rate at which time passes can depend on how you move and where you are. A clock in a fast-moving spaceship will tick more slowly than an identical clock left on Earth. A clock sitting in a strong gravitational field, such as near a massive planet, will tick more slowly than a clock far away from any mass. These effects are not speculation. They have been measured with atomic clocks on airplanes, in satellites, and in laboratories. Without accounting for them, the navigation systems you use every day would drift out of sync already. This is a kind of time travel, not the cinematic kind where you walk into a machine and step out in a different century, but a real, modest offset in lived duration. If you travel on a high-speed journey and return, you will be slightly younger than the twin who stayed home. The difference is usually tiny, but in principle it can be made large. If you could build a ship that moves extremely close to the speed of light and maintain that speed for a long stretch, time on board would slow dramatically relative to Earth. You could leave, circle the galaxy, and return to find that many generations had passed at home while only a few years had passed for you. This is time travel to the future. One way. It does not violate any known laws. It simply exploits the geometry of space-time, your own proper time, the time measured along your world line. Your personal path through space-time remains smooth and ordinary. You always feel 1 second following another in the same way. It is only when you compare your path to someone else's that the mismatch appears. From their perspective, you skipped ahead. Travel to the past is much more troublesome. In everyday language, going to the past means finding a path through space-time that leaves an event and then returns to that same event, or to an earlier one, in such a way that you could interact with it. In technical terms, this would be a closed time-like curve. Closed, because the path loops back on itself. Time-like, because it always moves forward locally according to the traveler's own clock. A closed time-like curve is a path that allows you to go forward in time at every step and still end up where you started. The equations of general relativity, taken purely as mathematics, do admit solutions that contain such curves. There are models of rotating universes where the overall twist of space-time allows world lines to circle back. There are hypothetical configurations of matter, like infinitely long, dense cylinders spinning at extreme rates, that seem to create regions where closed time-like curves exist. There are carefully constructed wormhole setups, where, by moving one mouth relative to the other and then passing through, you can, in the equations, come out before you went in. These constructions are fragile. Many require idealized conditions that almost certainly do not exist in our universe: infinite lengths, perfectly smooth matter, exact symmetries. Others seem to break down when small disturbances are added, or when quantum effects are taken into account. There are conjectures, not proven but widely considered, that some deeper principle forbids the formation of time machines in any realistic situation. One famous phrase for this is chronological protection, the idea that the laws of physics protect causality from being violated. Even if you set aside those worries and treat closed time-like curves as possible, you immediately encounter paradoxes. The most famous is simple. If you go back and change something that is a condition of your own existence, what happens? If you traveled to the past and prevented your grandparents from meeting, you would never be born. If you are never born, you cannot travel back to interfere. If you do not interfere, they meet and you are born. The loop has no consistent state. You oscillate between competing realities. There are a few ways people have tried to soften this. One is to insist on consistency. According to the self-consistency principle, any event that happens on a closed time-like curve must be part of a single, globally consistent history. You can travel to the past, but anything you do there was always part of what happened. You cannot kill your grandparents, because the universe you come from already includes the fact that you tried and failed, or were prevented. You might go back with the intention to change things and find yourself constantly thwarted by circumstances that conspire to keep the timeline self-consistent. Another option is to widen the stage. In a multiverse, or many worlds setting, traveling to the past might mean hopping to a different branch of reality. You arrive in a history that looks like your own but is not identical. You can change events there without affecting the branch you came from. You do not erase your own origin. You simply create or move into a different thread of the larger tapestry. In that picture, there is no contradiction. There is only an increase in the number of branches. Both of these resolutions say something similar in different languages. You cannot have a single line of events that is both changed and not changed. Either the line is fixed and your actions are folded into it, or there are many lines and you jump between them. The paradox arises only if you try to have it both ways at once. There is another, quieter way to think about time, called the block universe picture. In this view, inspired by relativity, all moments of time exist together in a four-dimensional structure. Past, present, and future are just different slices of the same block. Your sense of moving from earlier to later is like the experience of a spotlight drifting along a film reel. The reel is all there at once. The story feels like it is unfolding, but the frames already exist. From this perspective, the question, "Can you travel to the past?" becomes strange. You are already located at each point along your world line. There is no external place from which you could jump to a different point. Time travel, in the fictional sense, would require stepping outside the block entirely, and our current physics has no room for that. This can feel suffocating. If all events are laid out in a fixed structure, where is freedom? Where is the possibility of doing otherwise? One response is to say that even in a block universe, you do not know the future in advance. From your internal perspective, choices feel open. You experience deliberation, uncertainty, decision. The fact that, in some abstract representation, your entire life is a single curve, does not change the lived reality of moving along that curve one moment at a time. Another response is to question whether the block picture is the only valid reading of the mathematics. Maybe the equations do not, by themselves, decide whether time is static or genuinely unfolding. If you bring quantum theory into the conversation, the ground shifts again. Quantum mechanics includes a kind of built-in randomness. When you measure a system, the outcome is not determined in advance. In the same way, a coin with a tiny bias, there is a sense in which the future is genuinely open within certain probabilities. How that openness meshes with the smooth determinism of relativity is one of the deepest unresolved questions in physics. It matters for time travel because it touches on whether the future is already there, waiting, or whether it is partially created as events happen. The simulation story offers an easy answer, but only on the surface. In a computer program, you can pause, rewind, branch, and replay. Time is just a parameter the system advances. A developer can step outside the running process, load a previous save, and run things differently. From the character's point of view, this would look like someone rewriting history. Their memories would not match the deeper log. In that environment, time travel is a matter of permission, not law. If we were in such a system, the inability to access these features from the inside would not prove they do not exist. You cannot, from within a game, call functions you do not have access to. You can only infer, from occasional glitches or unexplained resets, that there might be layers of control you cannot see. In our universe, we do not observe clean rewinds. We do not see objects jump back to earlier states in defiance of entropy. What we do see are fragile systems of memory and record keeping, all of which can fail. Forgetting is not time travel. It is just loss. And yet, subjectively, you already live as a time traveler of sorts. You carry past events forward as memories and project future events backward as plans and fears. You rehearse conversations that have not happened. You revisit scenes that have. Entire hours of your waking life are spent in simulated times that do not exist outside your mind. None of this changes the external sequence of events, but it does change how you inhabit them. The hard edge of physics says, you cannot go back to your own childhood. You cannot step outside your own history and edit it. You cannot fast forward to your own death and then return with spoiler knowledge. The softer, human edge says, you are still responsible for how you relate to the fact that time only goes one way for you. Regret is, in a sense, a wish for time travel. So is nostalgia. So is the hope that, someday, things will be better. When you picture yourself in the future, you are trying, in a limited way, to send a message forward from the present. Here is what I want you to do differently. In that sense, the instability of time is not just in wormholes and paradoxes. It is in the gap between what the equations allow and what your life permits. Between the intellectual possibility of world lines that loop and the emotional reality of a single line that does not. Physics tells you that time can dilate, mix with space, stretch near massive objects. Stories tell you that time can be folded, revisited, escaped. Your body tells you that time is a narrowing corridor with a door at the end that opens only one way. Whether or not anyone, anywhere, ever builds a time machine is almost irrelevant to the deeper discomfort. The discomfort comes from realizing that even in the most generous reading of our theories, your access to time is radically asymmetric. You remember backwards. You anticipate forwards. You act now. Everything else is either trace or speculation. For a being who is aware of their own ending, that asymmetry is not a technical detail. It is the background against which every choice is made. When you live inside a corridor that only goes in one direction, every attempt to probe the walls feels dangerous, especially when the people doing the probing are aiming not at comfort, but at the foundations. Physicists have a dry phrase for something that, to the rest of us, sounds like magic. They call it higher dimensional embedding. Popular culture found a better name: hyperspace. In cartoons and science fiction, hyperspace is the place you duck into when you want to cheat distance or time. A sideways route through a level of reality that ordinary people cannot see. The strange part is that when you strip away the sound effects and glowing tunnels, the core idea is not so far from what serious physics entertains. Imagine again that flat being drawn on a sheet of paper. For that being, there are only two directions that make sense: along and across the page. If you lift the drawing gently into the air, you are moving them through a direction that does not exist in their vocabulary. They would not experience a graceful ascent. They would experience disappearance and reappearance, or something even harder to describe. From their point of view, the space where they live is complete. From your point of view, it is a thin layer in a thicker world. When physicists talk about extra dimensions, they are talking about something like that. Not vague realms of spirit, not fantasy kingdoms, but additional directions in the mathematical description of space-time. The equations they work with do not care that your intuition stops at up, down, left, right, forward, and back. If the math works more cleanly with more coordinates, they will use more coordinates. Whether those extra directions are physically real in a way you could traverse is a harder question. Now place this idea next to a real machine. On the border between Switzerland and France, buried underground in a ring that stretches across the landscape far beyond what any one person can see at once, lies the Large Hadron Collider operated by CERN. It is a particle accelerator, a device that uses electric fields to push protons to speeds incredibly close to the speed of light and then smash them together. Around the ring sit detectors, enormous instruments layered with sensors, waiting to record the debris. From the inside, meaning from the point of view of the people who work there, this is an instrument of measurement. They are testing how matter behaves at energies higher than anything we can reach in ordinary conditions on Earth, looking for particles and interactions that reveal how the universe is built. From the outside, for many, it looks like a door being pushed. It is not hard to see why. The imagery is potent. A giant ring underground, invisible beams of particles racing in circles, collisions so energetic that they recreate conditions similar to those shortly after the beginning of the universe. The language used to describe the goals sounds like an invitation to fear, probing extra dimensions, searching for miniature black holes, exploring the unknown. If you already feel that reality is fragile, words like that do not reassure you. Rumors began to circulate that the collider might do more than reveal structure, that it might tear it. People worried that the collisions could create a black hole that would fall to the center of the Earth and consume the planet. Others whispered about portals to other universes, cracks in the fabric of space-time, doors to hyperspace that could not be closed. Lawsuits were filed. Public hearings were held. Committees wrote reports explaining why these scenarios were not just unlikely, but incompatible with what we know. The arguments were simple and sober. Nature has been doing cosmic ray experiments for longer than Earth has existed, all over the universe, and constantly in our own atmosphere. Particles from distant galaxies slam into matter at energies far exceeding what the collider can achieve. If such collisions could create dangerous black holes or tear open stable portals, those effects would already have happened. Planets would not form. Stars would not last. The sky would look different, or would not exist at all. The fact that we are here to worry about the collider is itself quiet evidence that the energies it uses are safe on cosmic scales. Miniature black holes, if they can be produced at all in such machines, would be incredibly tiny and unstable. According to our current understanding, they would evaporate almost instantly in a flash of radiation. long before they could grow or interact with anything in a meaningful way. As for extra dimensions, the collider can, at best, infer their presence indirectly through missing energy in collisions or subtle patterns in the debris. It cannot send a camera into them. It cannot pry them open. And yet, the fear persists. Part of that fear is simple unfamiliarity with the science. Part of it is something deeper. When you hear that a group of people are deliberately recreating extreme conditions, testing the edges of what is possible, it is hard not to project onto them every story you have ever heard about doors that should not be opened. Hyperspace, in fiction, is rarely just a neutral transit system. It is haunted. There are things that live there. There are routes you must not take, coordinates you must not use. Behind that is a more basic anxiety, that the world has layers not meant for you, and that trying to access them is a kind of trespass. The collider at CERN is, for some, the real-world embodiment of that trespass, a visible symbol of humanity pressing against the boundaries of its own simulation, if you choose that metaphor. But look more closely at what is actually happening there. Each collision is not a violent blow against the walls of the universe. It is a tiny, localized rearrangement of energy. The detectors do not reach into hyperspace. They surround a small volume and count patterns in the particles that fly out. What they are really doing is mapping regularities. They are asking, in a controlled way, what combinations of energy and momentum are allowed and which are forbidden. If extra dimensions exist and affect these patterns, they will leave signatures. Energy might seem to vanish into directions we do not see. Forces might weaken at small scales in ways that indicate spreading into a larger volume. These would be clues, not gateways. Learning that there is a staircase behind a wall is not the same thing as breaking through and climbing it. The fear of doors often hides a different fear, that the room you are in is all there is. If CERN and experiments like it find no evidence of extra dimensions, no hint of new symmetries, no surprising departures from known physics, some people will feel relief. Others will feel a strange kind of claustrophobia. The universe will seem more finished, more closed. The script more complete than they had hoped. From an existential point of view, both outcomes are unsettling. If there are hidden layers and we discover them, then we must confront the fact that we have been living in a simplified cross-section of a more complex structure, and that our intuitions about reality are even less trustworthy than they seemed. If there are no new layers within reach, then we must face the possibility that the rules we have are, for practical purposes, final, and that the walls of our world are thicker than we imagined. In both cases, the collider becomes a mirror. We project onto it our hope that reality is richer than it appears, and our fear that it is too rich. We imagine it opening doors, and we imagine it slamming them shut. In truth, it is a machine that takes data. The meanings we wrap around it are ours. There is one more layer to this. When you watch simulations of particle collisions, rendered as bright lines and spirals on screens, you are already inhabiting a simulation of a simulation. The underlying event is mathematical, described by probabilities and fields. The detectors turn that into electronic signals. Computers turn those signals into images. You, sitting at home, watching a visualization online, see a graphic representation of those images. At each stage, distance from the original event increases, and yet your sense of contact with the fundamental grows. This is where hyperspace, CERN, and the simulation question intersect in a quiet way, not in disasters or portals, but in the realization that your access to the deep structure of reality is always mediated, always indirect. Whether the universe is ultimately continuous fields in higher dimensions or discrete information on some deeper substrate, you never touch it raw. You touch graphs, counts, pictures, and words. You touch interpretations. So when people worry that the collider might open a door it cannot close, they are, on some level, right. Not in the sense of tearing a literal hole in space-time, in the sense that every serious attempt to probe the foundations opens a conceptual door that does not shut afterwards. Once you have seen how strange the rules can be, you cannot unsee it. Once you know that extra dimensions, hidden symmetries, or new particles are at least coherent possibilities, you cannot go back to believing that the stage under your feet was designed only for you. The larger fear, the one that lingers after the headlines fade, is simpler. It is the fear that we are touching something we do not understand with tools we barely control, inside a reality whose depth we cannot measure. And that, whether or not there are doors to hyperspace, the act of looking for them will leave us unable to trust the walls in quite the same way ever again. When you start to doubt the stability of walls and doors at the deepest physical level, it becomes harder to dismiss the small, private moments when the room you live in seems to quietly twist. Most people do not encounter black holes or particle accelerators. They encounter something else, a voice in an empty house, a clock that skips, a day that does not line up with memory, a feeling that you have already stood in this exact place, heard this exact sentence, watched this exact gesture, even though every reasonable story about time says you have not. In the language of physics, these are anecdotes. In the language of the people who live them, they are cracks. It is easy, and often correct, to explain such moments in psychological terms. The brain is not a camera, it is a pattern-making machine, constantly predicting what will happen next and updating those predictions when it is wrong. When the prediction and the input line up too well, you get a feeling of eerie repetition. When they clash, you get surprise, discomfort, or fear. Most supposed glitches in reality can be traced back to glitches in that prediction system, but not all of them are easy to file away so neatly. And the difficulty of doing so is part of what keeps the idea of a simulated or layered reality alive. Start with a classic, the haunted room. Someone moves into an old house and hears footsteps in the hallway at night when no one else is home. Or they see, just at the edge of perception, a figure standing at the foot of the bed, which vanishes when the light comes on. They report objects moved, whispers, knocks, cold spots. The usual skeptical explanation points to drafts, building noises, the way old wood shifts and creaks, the way light from outside can throw shadows that look like people. It mentions sleep paralysis, a state where your body is still paralyzed from dreaming while your mind is half awake, often accompanied by vivid, frightening hallucinations. It mentions suggestion. Once someone tells you a place is haunted, you begin to notice every small anomaly and fit it into that script. All of this is true as far as it goes. We know that human perception is vulnerable to context. In experiments, people shown ambiguous images will interpret them differently depending on what they have recently been told or primed to expect. In a dark, unfamiliar environment, the threshold for calling something a presence drops. The mind would rather see an agent where there is none than miss a real threat. This bias toward agency is a survival feature in the wild. In a quiet bedroom, it becomes ghosts. Yet if you listen carefully to people describing their experiences, you notice something else. They are not merely saying, "I heard a noise." They are saying, "The noise did not behave the way the world usually behaves." A door opened without a draft. A voice spoke a sentence that carried meaning. A clock stopped at the exact moment someone died. These are not just sensory anomalies. They are narrative anomalies. They feel like events that belong to a different story bleeding into this one. From a simulation point of view, it is tempting to treat such moments as bugs. A non-player character spawned in the wrong place. A sound loop triggered without a cause. A variable overwritten. The difficulty is that our data about these events is poor. There are no controlled repeats, no consistent measurements, just human testimony. Memory is malleable. Stories are polished in the retelling. The more unusual the report, the more likely it has been reshaped by attention and time. The line between evidence of an external glitch and evidence of internal construction is blurred. Consider another category: missing time. Someone is driving a familiar road at night. They remember passing a landmark. Then the next thing they know, they are many kilometers farther along, with little or no memory of the stretch between. Or a group of friends spend an evening together, and later one insists that hours are unaccounted for, while others recall the night as ordinary. In extreme versions, people interpret this as abduction, as contact with non-human entities, as removal from the normal flow of time. Here again, psychology offers tools. There is a phenomenon called highway hypnosis, where a driver on a monotonous road loses conscious awareness of the details of driving. Operating almost on autopilot, they can respond to changes and reach their destination safely, but later have sparse memories of the trip. Something similar happens when you are deeply absorbed in thought or in a task. Time feels as if it has compressed. An hour can feel like a few minutes. At the other end, in situations of fear or trauma, time can feel stretched, with moments frozen into excruciating detail. The brain is constantly reconstructing the sense of duration from a patchwork of events, emotions, and bodily signals. There is no master clock. There is only a process that stitches experiences into an ordered story. When that stitching goes wrong, you feel it as missing time, or as time that will not move. In most cases, there is no need to invoke altered physics. Altered narrative is enough, but the fact that time is assembled inside your mind, rather than handed to you as a fixed film, is itself unsettling. It means your sense that reality flows smoothly is a result of neural bookkeeping, not a direct perception of the external world. You could, in principle, live your entire life with a slightly misaligned internal clock and never know. Your only access to how long something took is memory, and memory is not as solid as it feels. This brings us to one of the strangest collective glitches, the so-called Mandela effect. The name refers to cases where large groups of people remember the same detail in the same wrong way. A logo that many recall as having one shape turns out, on inspection, to have another. A famous line in a film is remembered with a different wording than the actual recording. People are certain they remember a public figure dying in one decade, only to find that person alive years later, or that the actual date of death is different from what they recall. The phenomenon is named after a specific case where some people reported vivid memories of the South African leader Nelson Mandela dying in prison long before his real death as an elder statesman. Faced with this, there are two broad stories you can tell. One is purely psychological. Human memory is reconstructive, not reproductive. Every time you recall something, you rebuild it from pieces, influenced by other memories, by expectations, and by how that story has been told to you. Popular culture can seed the same mistaken version into many minds. People talk to each other and align their recollections. The result is an illusion of shared access to an alternate timeline, when in fact they are sharing a common error. The other story treats the shared wrongness as a clue. Perhaps there are branches, and sometimes information leaks sideways. In that reading, the Mandela effect is a smudge where two close realities have rubbed against each other, leaving behind conflicting traces in memory. You remember both, but the world now presents only one as true. The glitch is not in your brain. The glitch is in the version history of reality. It is important to say that there is no hard evidence for that second story. We do not see physical records flicker between versions. We do not see archival footage rewrite itself. What we see are human beings insisting that their memories do not match the records. and interpreting that mismatch through whatever metaphors are available. The safer conclusion is that the brain is less reliable than it claims. The more haunting conclusion is that, even if reality is stable, you have no way from the inside to be absolutely sure. Some of the most intense reported glitches happen at the boundary between life and death, near-death experiences. People who have been clinically close to dying, sometimes resuscitated after the heart stops for a short time, often describe vivid experiences. A sense of leaving the body and looking down from above, traveling through a tunnel toward a bright light, meeting deceased relatives or beings of great significance, reviewing their entire life in an instant, feeling an overwhelming calm or a command to return. Neuroscience approaches these reports with caution and respect. There are plausible mechanisms for many of the features described. Lack of oxygen to the brain, called hypoxia, can produce tunnel vision, literal narrowing of the visual field that the mind may interpret symbolically as a tunnel. Changes in brain chemistry during extreme stress can generate feelings of euphoria or awe. The temporal lobe, a region of the brain involved in processing memory, emotion, and certain aspects of perception, is particularly sensitive to abnormal electrical activity. Stimulation there can produce sensations of presence, out-of-body experiences, and profound meaning. There is evidence that the brain remains active for a short window after the heart stops, and that waves of activity can occur during that window. It is not unreasonable to suppose that some near-death experiences are the brain's final attempts to make sense of massive disruption. The life review could be memory systems firing in rapid, disorganized bursts. The presence of guiding figures could be the mind reaching for comforting images under extreme threat. And yet, there are details that refuse to sit quietly. Some people report verifiable observations that, in theory, they should not have been able to make from the vantage point of an unconscious body. Descriptions of conversations in adjacent rooms, noticing the placement of objects that were out of their normal line of sight. These accounts are rare and contentious, and subject to the same memory issues as any story told after the fact. They do not overturn neurology, but they mean that anyone serious must admit that we do not fully understand what consciousness is capable of under extreme conditions. If you see the world as a simulation, near-death experiences take on a different flavor. They become a kind of boundary experience, like what happens to a game character when they reach the edge of the map or when the program is about to terminate their instance. The tunnel is an exit animation. The life review is a data dump. The choice to return or not is a prompt from a higher process. This is an attractive metaphor, because it turns personal crisis into a system-level event. It says, you are not just a body shutting down. You are an avatar being evaluated. The danger in that metaphor is that it can make you careless with reality. If you treat death as logging off, you may be tempted to treat life as an experiment with no weight, whatever the deep nature of consciousness turns out to be. We know at least this, from the inside. Your experience of dying will be final. There is no guarantee of a reset button. There is no evidence of a lobby where you can review your performance. Even if something of you persists, it will not be you in the way you are now. With these specific memories and attachments, the glitch at the boundary does not free you from responsibility inside the boundary. Then there is déjà vu, the everyday ghost. You step into a hallway in a building you have never visited, and a wave of recognition hits you, or someone says a sentence in a particular tone of voice, and you know exactly which sentence will follow, before they speak it, and then they do. It is a small thing, easily brushed off, but it can feel like an echo of another path, another run through the same scene. Cognitive science has several proposed explanations. One is that déjà vu arises when the brain's system for checking familiarity misfires. Normally, when you encounter something, different parts of the brain handle what it is and whether you have seen it before. If the "this is familiar" signal is triggered for a scene that is actually new, you feel déjà vu. Another idea is that a small delay or glitch between two processing streams can make the second pass feel like repetition. The scene is processed twice in quick succession, and the second time is tagged as memory rather than fresh perception. These accounts are plausible and supported by some evidence. They treat déjà vu as a timing error in a complex circuit, not as a message from another timeline. Yet the subjective flavor of déjà vu is stubborn. It feels less like simple familiarity and more like an almost recalled dream or an alternate branch. It is as if, for a split second, your experience of the present overlaps with another version of the present that almost happened, and your mind, unable to hold both, compresses the clash into the single feeling of, "I have been here before. It was relive." This is where existential questions seep back in. In all these phenomena, hauntings, missing time, collective false memories, near-death experiences, déjà vu, you are caught between two kinds of humility. One is humility about your mind. You must admit that your perception and memory are limited, biased, and prone to error. The other is humility about your access to reality. You must admit that even if something truly strange happened, your tools for detecting it are built out of the same fallible stuff. Physics, for all its power, does not rescue you from this gap. It can tell you that certain claims are incompatible with conservation laws or with the finite speed of light. It can tell you that the energies involved in your living room are not enough to spontaneously open wormholes. It can measure brain activity and correlate it with reports of visions. It cannot, at least not yet, reach into a moment of terror at 3 in the morning and decisively label it illusion or contact. The raw experience happens at a scale where subjective and objective are entangled. The simulation idea, brought into this terrain, becomes less a claim and more a mood. It says, perhaps these glitches are not about ghosts, aliens, or souls in the traditional sense. Perhaps they are about boundaries, places where the mapping from a deeper level to the level you inhabit is imperfect, or where the system adjusts in ways that create temporary inconsistencies in your story. It offers a way to think about weirdness without immediately reaching for old mythologies. But it also does something more destabilizing. It reminds you that even if every single paranormal report were explained tomorrow by brain chemistry and social contagion, the deeper question would remain untouched. You would still be an observer trapped inside a system, with no external vantage point from which to verify that the system is what it appears to be. You would still be forced to build your picture of reality from patterns in your experiences, knowing that both the patterns and the experiences are processed through machinery you did not design. So, are paranormal glitches evidence or illusion? In the strict scientific sense, most are illusions, misinterpretations, memory distortions, and the byproducts of brains evolved for survival, not for metaphysical accuracy. A small remainder sit in a gray zone, not because they clearly point to another layer of reality, but because our current theories are not fine-grained enough to account for every detail of every report. There is no robust, repeatable experiment that shows a ghost or a timeline shift on demand. Yet, even as illusions, they are evidence of something important. They show you the seams in your own construction of the world. They reveal how eager you are to treat meaning as something the universe must be projecting at you, rather than something you are actively weaving. They expose the discomfort you feel when confronted with events that do not fit your internal model, and the lengths you will go, either toward belief or toward dismissal, to patch that model. In a sense, the most honest position is the least satisfying one. You can say, for now, there is no compelling scientific reason to treat paranormal glitches as proof of a simulation or of hidden realms breaking through. And at the same time, you can say, the persistence of such experiences, across cultures and eras, is a reminder that the border between inner and outer, between mind and world, is not as sharp as we like to think. We live at that border all the time. We call it reality. Maybe the strangest part is that nothing in your daily life changes. You will still wake up, check your messages, worry about work, think about someone you miss, grow older. The buses will not start phasing through buildings. The sky will not turn into code. Whatever the deep structure of reality is, it continues to express itself through coffee, traffic, invoices, quiet arguments in kitchens at midnight. And yet, once you have seen how loose the word real becomes under pressure, it is hard to return to the old kind of certainty, the multiverse, quantum branching, hidden dimensions, wormholes that almost exist, black holes that refuse to confess what they do with information, distances that turn the galaxy into scenery, time that warps instead of flowing, glitches of perception that feel like messages from somewhere else. All of it points toward the same quiet fact. From inside a system, you do not get to see the system. You see regularities. You write down equations that track them. You build devices that extend your senses. And then you build theories to explain what those devices show. Sometimes the theories contradict your intuition so completely that you have to choose between comfort and coherence. Sometimes they contradict each other. In all cases, they remain maps. Beautiful, powerful, limited. Maybe we are in a simulation. Maybe we are in a single, self-existing universe with no outside at all. Maybe the distinction is less meaningful than it sounds, because any reality that can host beings like us will, from their point of view, feel like a world they cannot step beyond. You do not get to know, from the inside, what the whole thing is. What you do get is this: a brief window of consciousness in which you can notice that the window exists. The ability to ask careful questions in a place that may never answer them. The responsibility to act as if your choices matter, even if the stage beneath you is opaque. Perhaps that is the system we were never meant to see. Not the machinery under reality, but the fact that we are here at all, watching something we cannot name, and calling it a life.